that will be today's lesson. So today we're, wrong, crazy thing. Today we're doing gravitational potential energy. We talked about the work energy theorem and we talked about kinetic energy, those two ideas, where kinetic energy was energy of motion, and work, remember, work was the force times the distance. And then you put them together and that gave you the work energy theorem. And the work energy theorem stated, why is this going? The work energy theorem was work equals delta K. So the amount of work you put in changes the kinetic energy. So the kinetic energy is energy of motion, that's that delta K. Potential energy, gravitational potential energy, this is stored energy. And we use a U for stored energy, right? For gravitational potential energy. And this is going to be mass times gravity times delta Y. A lot of times you'll have it see it as mgh, where h is your height, which is the same thing as delta Y. So this is your stored energy. And remember our equation from the kinematics, v squared equals v naught squared plus 2g y minus y naught. Well, remember what kinetic energy is. Kinetic energy is K was 1/2 mv squared. So if I put these two equations together, you can see that v squared minus v naught squared over, oops, that's not the right thing. Over right, if I add an m in front of both of those, you can see the change in kinetic energy, delta K, equals the change in potential energy, which equals the work done. So the work can be done to change your kinetic energy to speed you up, or you can do work like when you're lifting a box. So, right, you do work in that case, you're moving a force over a distance, and now that box, when it gets up here, it has potential energy because that box can fall and do work. So this idea, this relationship between work and energy still holds true, even potential energy. Here's our formula, U equals mgh. And you can see that, oh boy, you can see here, U equals mgh, that's our formula for potential energy. And over here we have two televisions. This is what an old television used to look like. You guys probably aren't used to that, but an old television was very big and very heavy. And you could get it up by using a pulley system or by going up the stairs. When you get it up to that height, whatever height it happens to be, let's say this height here, it doesn't matter how you get from A to B or from the top to the bottom, right? They're actually using this height up here, so we'll stick with that. So it doesn't matter how you get from A to B. All that matters is once you get to that height, now you have an H, you have a mass, and that gives you a potential energy at that height. And if you were to drop that television, it would fall down, and right before it hits the ground, it would have a velocity. So the potential energy here would equal your kinetic energy here. We say the delta U equals delta K. The change in potential energy is going to equal your change in kinetic energy. This again just reaffirms this idea. The energy you put in is going to equal what you get out. So you put in work to lift up the acorn, right? If you have a winding clock like this, you put in work to lift up the acorn, and then once it gets to the top, the acorn falls back down. Gravity does the work and spins the gears inside here. So these gears spin around and then your clock spins. So the idea is you have to put work in to get energy. Oh no, what happened? And this gives us the law of conservation of energy. It's a law that means it holds true everywhere. It's always true in every sense. And this tells us the total energy at the beginning equals the total energy at the end. Whatever energy you have to start is going to be your final energy value. And at all points, the total energy is equal to U plus K. Initial equals final. Initial U plus K, right, needs to be grouped together, equals final U plus K. The total energy stays constant. That's the law of conservation of energy. Matter cannot be created or destroyed. All the matter you have in the beginning equals all the matter you have at the end. Same thing with a pendulum. Later this semester, we'll do a pendulum lab. But here at point A, UA naught plus, or UA I can just say because there's no, we don't need a naught there. But UA plus KA equals UB plus KB, which equals UC plus KC. Now at point here, right, the kinetic energy is zero, it's not moving. At this point, potential energy is zero. And then back up here again, the kinetic energy is zero. So at each different point, you're either going to have potential or kinetic based on whether or not the object's moving. At every single point between A, B, and C, the total energy remains the same. UA, U plus B, or excuse me, U plus K is always constant. To change an object's energy, remember, you need to do work. So whatever is happening here, gravity is doing work on this to change the energy. Gravity is the force that causes work to be done. Same thing with a roller coaster. If you have a roller coaster and, oh my goodness, this thing has a mind of its own sometimes. If you have a roller coaster, the problem is I can't get the pen thing to come up unless I tap on it. There it is. If you have a roller coaster and you're at the top of the roller coaster, right, here's your maximum U, U max. At your lowest point down here, this would be K max. So we would say mgy minus y naught. And then we have down here, 1/2 mv squared. This would be 0, right? So at the top, we would say mgy equals 1/2 mv squared. And this is how we could find the velocity at the bottom. These m's cancel out, and you have v squared equals 2gy. V equals the square of 2gy, or h. A lot of times we just call this an h for height. Whenever you see h, that means delta y. All right, so let's take a look at a problem. How much more gravitational potential energy does a 1 kilogram hammer have when it's on a shelf 1.2 meters high than when it's on a shelf 0.9 meters high? So we'll just do this real easy, right? If I build a shelf here and I lay my hammer on it. That's a hammer, 3D, really bad, but it's there. So my hammer's on the shelf. And the first shelf is 0.9 meters. And then our second shelf is up here. What happened? And that would be 1.2 meters. And we're looking for how much more potential energy. So we'll say that this is YA, and we can call this YB. So UA equals MGYA. UA equals 1 times 9.8 times 0.9. UA equals 8.82 joules. Units for energy are joules, remember? And then UB is going to equal MGYB. UB equals 1 times 9.8 times 1.2. 11.76. So delta U equals 11.76 minus 8.82. 2.94 joules. which is the same thing as saying mg yb minus ya.
I have a question.
Yeah.
So, oh, never mind. It's written out in the example itself. I was gonna ask why you took 1 times 9.8, but I just read that it was the weight of the hammer. Never mind.
All right, cool. Yep, mass of the hammer, 1 kilograms. I gotta get through all this. Sorry, all those things pop up. Here's another problem. What's the final speed of the roller coaster if it starts from rest at the top of the 20-meter hill and work done by frictional forces is negligible? What is the final speed and assuming the initial speed? So let's do the first one. What's the final speed of the roller coaster if it starts from rest? V naught equals 0. And we're coming down here, right? So V naught to 20 meters. What is the final speed? So I don't have a ton of room on this page because of the giant picture, but U equals M. I don't want that formula. This is a conservation of energy formula. So we'll say K at the top. I don't want to do that either, sorry. U at the top. I'm freaking out because I don't have a lot of room to write here, so I'm just kind of mess. U at the top equals U at the bottom. So this is the top or the start, and then this would be the bottom, the finish. So U at the top equals U. Oh my goodness, guys. I'm not E at the top. The total energy at the top equals the total energy at the bottom. Sorry, it's Monday. So U at the top plus K at the top equals U at the bottom times plus K at the bottom. Now, potential energy at the top, the velocity is 0, so it has no kinetic energy. We're going to call this our reference point, the bottom. So this is height equals 0. So that means your potential energy at the 0 or at the bottom equals 0. So essentially our equation is mgy equals 1/2 mv squared. Because v naught is 0 and y naught. I should call this y naught, sorry. Y naught is 0. We'll call this y. So my goal is to find v, right? It says, what is the final speed? So our masses cancel, and we have v squared equals 2gy, and I'm just going to move it up here because I ran out of room. V equals the square of 2gy. This is a pretty common formula that we use, V equals the square root of 2gy. So V equals the square root of 2 times 9.8 times 20. Basically 19.80 meters per second. That's our final velocity. Any questions there? Now, if we do this again in part B says, what's the final velocity if the initial speed is 5? So we got to erase all this because I don't have a ton of room here because of this giant roller coaster. So this time we do have a kinetic energy at the top because it's moving. We don't have a potential energy at the bottom. So here we have mgy plus 1/2 mv naught squared equals 1/2 mv squared. Well, the m's cancel. Can multiply through by 2, so that gives me 2gy plus v naught squared equals v squared. That should look like a kinematic, right? V squared equals v naught squared plus 2g Y minus Y naught. There's our kinematic equation. That's where that comes from. It comes from the law of conservation of energy. So now we just plug in what we know. V squared equals 5 squared plus 2 times 9.8 times 20. You hope it going faster, right? 20.42 meters per second. 20.42. Anybody have any questions on that one? All right. The floor of a basement of the house is 3 meters below ground level, and the floor of the attic is 4.5 meters above ground level. What are the respective potential energies of 1.5 kilogram objects in the basement and attic relative to the ground level? What is the change in potential energy if it's moved? So here's our house. I drew it out for you. This is what it looks like. What we want to find are the potential energies of a 1.5 kilogram object relative to the ground level. So we're going to just call this 1, 0, and 2. So we want to find U2. So that's mg y2. U2 equals, that's a U, equals 1.5 times 9.8 times 4.5. U2 equals 44.1 joules. Now, U1 is equal to mgy1. U1 equals 1.5 times 9.8 times negative 3. U1 is oh, is this 44.1? Did I put the wrong values in? Yeah, sorry, this is negative 44.1 joules. That first one. Oh my goodness, would this thing stop? I just want to see the eraser. 66.2 joules, sorry. Notice that U1 is negative. U1 is negative. It's negative because it's relative to our reference level here. It's relative to the reference level. So you can have a negative potential energy if you base it on your zero position. That's what you want to look at. You want to look at your zero position and refer where you're at to your zero position. So a positive potential energy means you're going above, and negative potential energy means that you're going below. So if an object is going in part B from the attic to the basement, so we're going from up here to down here. So are we gaining potential energy or losing potential energy by going down? That's the question you need to ask yourself. So what we have is our delta U is U1 minus U2, final minus initial. So delta U is negative 44.1 minus 66.2. Delta U is 110.25. Do you have any questions on there, on what we did so far? Anybody have anything they need clarified here?
So what does it mean when you do like negative work?
Negative work, remember, negative work means that you're slowing something down. So in this case, we're lowering its potential. It has less potential in the basement than it does in the attic. So we're losing potential energy in here. So we'd be doing negative work on the object. Does that make sense?
I guess, I mean, it's kind of confusing because like, you're still doing the work. I'm just kind of confused. Why is it negative? I mean, I get it because the force is down on it, but like the work's still there.
I think it's a matter of just the direction. Think like X and Y values, how going up is positive and going down is negative, kind of like that.
Well, remember, work is a scalar, so it's not based on the Cartesian coordinate system. It's based on whether it's gaining or losing. So if it's gaining speed or gaining height, that's positive work. If it's losing speed or losing height, that's negative work. So like gravity does negative work on an object. Your hands do positive work on an object when they lift something up.
Oh, I get it.
Does that make sense?
Yeah.
All right, so I got to get out of this crazy screen somehow. Sorry, there's a lot of clicking here. I don't know how. I want to go to the next slide. All right, so the next slide. A 0.3 kilogram ball is thrown vertically upward with an initial speed of 10 meters per second. If the potential energy is taken as zero, find the ball's kinetic potential and mechanical energies at the initial position, at 2.5 meters above, and at 5 meters, or 2.5 meters above, and at its maximum height, whatever that happens to be. So what happened in here is, well, I'm going to fill this. I don't want this chart. Get out of here. What's going to happen is we have a ball, and we're throwing this ball, and it's going up here to its maximum height. And along the way, there's a 2.5. Now, we don't know if it's halfway or a quarter of the way or 3/4 of the way. So I'm just going to put a random height in here. Y is equal to 2.50 meters. I don't know what height it is. We know the mass of the ball is 0.30 kilograms. And we know the initial velocity is 10.0 meters per second. So I'm going to make a grid. To fill in based on the mechanical, the potential, and the kinetic energy. So you want to use this chart. We're going to fill this chart in and determine each of these different values. So I'll get you started just so you have an idea of what I'm talking about here. And then you can go from there and figure out the rest of it. Let's start with the initial height or the initial position. We know at the initial position, the potential energy is 0. Oh no, where did it go? We know at the initial position, the potential energy is 0. We can find the kinetic energy. That's, oh, this thing is going to be a pain, isn't it? Let's make my own chart. Oh my goodness. All right, so here's our chart. We can see here that this is going to be 1/2 mv squared. So we have 1/2 times 0.3 times 10 squared. The kinetic energy on the ground is going to be 15 joules. Potential energy on the ground is 0 because it's down here at rest, or at the lowest point, I should say, not at rest. It's at its lowest point because y equals 0 at that point. And remember, the total energy at all points is U plus K. So E, the total energy is 0 plus 15 joules. So E for every column has to be 15 joules. 15 joules. That never changes. The total energy of the system is always the same. Now at 2.5 meters, we don't know the kinetic energy. We don't know how fast it's going. We do know the height though, so we can find U, mgy. So this is 0.3 times 9.8 times 2.5. 7.35 joules. That's U in the middle. And now to find KE, or kinetic energy, I don't think we used the E, but we use K. To find K, U equals K plus E. K plus E, what is that formula? That's not even a formula. E equals U plus K. So 15 equals 7.35 plus K. K equals 7.65 joules. Now, if we wanted to know how fast it was going at that point, right, we would just say V equals, K equals 1/2 mv squared, 7.65 times 2 divided 0.3 equals V squared. V equals 7.14 meters per second. So at our middle point, we're going 7.14 meters per second. Now for the final one, we know at the maximum height, what's the velocity? 0. So we know K is 15 joules. Oh, no. K is 0 joules. I'm losing my mind here. K is 0 joules. Velocity is 0, that means the kinetic energy is 0. So that means U has to be 15 joules at the middle point. Any questions there? So you can see the only place really where it's not 15 is at the arbitrary points in the middle. Every other point is 15 joules. At the top and the bottom, they just switch back and forth. And then any point in the middle, they're going to move between between 15 and 0. So as it goes up, the potential energy is going to go closer to 15. As it goes down, as it gains, or as it goes up in this case, the kinetic energy would go from 15 to 0. So at some point, I don't know what exact height it is, I would say it's probably a little bit higher than 2.5, maybe like 2.8. The K and the U would be equal to each other. But I don't know what that point happens to be. Any questions there? All right, let's try another one. Not this one. We'll do one more. Oh, this is the quiz. We're already at the quiz. This went really fast. Let's see if there's any in the book that I like. Get out of this crazy PowerPoint.
Yeah, the PowerPoint, I mean, the video is pretty short too.
Yeah, it's these lessons here in 7 and 8, I kind of stretched them out so that you could so it wasn't all, overwhelming all at once. So let's see if there's any in the book that are interesting that we can do here in chapter 7. Oh, well, let's make a problem up. Let's say I have a roller coaster. Here's what I want. I'm gonna make a roller coaster. All right, so here's my roller coaster. The mat, then we got a car up here, some people in it, and the mass of the car is, I don't know, 1,200 kilograms with the people in it and so on and so forth. On the top of the second hill, the velocity is 25 meters per second. This hill is 15 meters tall. How tall is the first hill? How tall is the first hill? Give that a try. See if you can figure that out. I can see you now, so give me the thumbs up if you think you got it right, or when you think you got it. The height of that hill. Anybody? We got a couple. All right, let's take a look at it. So we're going to use the conservation of energy. So U at the top plus the kinetic energy at the top equals U at the bottom plus the kinetic energy at the bottom. The kinetic energy at the top is the only one that disappears. So we have mgh, that's not the right thing, equals mg, we'll call this H1 and H2. H1, mgh1 plus 1/2 m v1 squared. We'll call that v1. M's cancel. H1 equals G, this is a 2 here, H2 plus 1/2 V1 squared all over G. G's cancel. H1 equals H2 plus 1/2 or 1 over 2 V1 squared. Oh, that's written so poorly. V1 squared over 2G. So H1 equals 15 plus 25 squared over 2 times 9.8. H1 equals 46.89 meters. Anybody get that right? Anybody get that right?
Yeah.
Good job. Anybody have any questions on that? Nobody has any questions? All right, let's try one more. Last problem for the quiz. We're going to try number 23 on page 261. And remember, work done by a spring is 1/2 K x squared. It says a pogo stick with a spring constant of 2.5 times 10 to the 4th newtons per meter, which can be compressed 12 centimeters. To what maximum height can a child jump on the stick using only the energy in the spring if the child and stick had a total mass of 40 kilograms? So let's write down our variables here. We know K is 2.5 times 10 to the 4th newtons per meter. We know that X is 0.12 meters. And we know the mass is 40 kilograms. And our goal is to find the maximum height. Give that a try. Does anybody have any questions? Are you done? Let me know.
What are we trying to find again?
We're trying to find the height. See it down here, the height.
Yeah.
You know, we were calling it Y. Y and H are pretty interchangeable in this chapter. All right, if you're having trouble with getting started, I'll show you here in a minute. Just hang tight. Remember, work equals delta U. So that means 1/2 kx squared equals mgy. Our goal is y. So kx squared divided by 2mg equals y. So 2.5 times 10 to the fourth times 0.12 squared over 2 times 40 times 9.8 equals y. .46 meters. That's as high as we can get. 1.5 feet. Anybody have any questions there? All right, we're going to take the quiz then. Last chance for questions before the quiz. All right, here's your quiz question. All right, I'm gonna switch back over to Zoom. Remember, send me a private chat with your answer. Hopefully you have that copied down. All right, Jackson, I got yours. $50 and $25, Jonah. 50 meters and 25 meters.